A projectile A is launched with a speed of 60 meters per second at an angle of 37 degrees with the x-axis measured anticlockwise. At the same time, another projectile B is launched with a speed of 80 meters per second at an angle of 53 degrees with the x-axis measured clockwise. We have to find their separation after a second. What would be the separation between A and B? It would be the displacement of B with respect to A after a second, or the other way around, that is, the displacement of A with respect to B. We follow exactly the same steps, that is, we attach a frame of reference to A, assume A to be at rest, find the initial displacement, velocity and acceleration of B in terms of A, and plug that into the equations of motion in order to obtain the unknown, which in this case is the final displacement. Let's look at projectile A first and express its velocity and acceleration in vector terms. The initial velocity would be 60 cos 37I plus 60 sin 37j after resolving the initial velocity vector. The acceleration acting on the projectile would be only the acceleration due to gravity, which can be expressed as minus 10j. There will not be any acceleration along the x direction or the I direction. Now let's obtain the initial velocity and acceleration for projectile B. Now we take a look at projectile B and express its velocity and acceleration in vector terms. The angle of launch as measured anticlockwise from the x-axis would be 180 minus 53, which is 127 degrees. So the initial velocity vector would be 80 cos of 127I plus 80 sin of 127j after resolving the initial velocity vector. And all the angles are measured with respect to the x-axis. The acceleration acting on the projectile will be only the acceleration due to gravity, which can be expressed as minus 10j. And there will not be any acceleration along the x direction or the I direction. So the acceleration of B will be identical to the acceleration of A. Now that we have obtained all the displacements, velocities and accelerations of A and B, let's proceed to attach the frame of reference to A and compute all the values of B with respect to A. The initial displacement of B with respect to A will be 0 since they start off together. The initial velocity of B with respect to A will be the initial velocity of B minus the initial velocity of A, or V0B minus V0A, which is minus 96.08I plus 27.76j. And the acceleration of B with respect to A will be 0, since they both have no acceleration along the x-axis, and they have an acceleration of minus g or minus 10 along the y-axis. And we know from the previous lessons that if two particles have the same acceleration, then one particle will see the other traveling in a straight line with a uniform velocity. So in this case, an initial velocity of minus 96.08 I plus 27.76 j would mean an angle of tan inverse of 27.76 over 96.08 plus 90 degrees, which is 164 degrees with the x-axis. And A would see B moving along a straight line and moving away at all times. So this is from A's frame of reference. But we have been asked to find the displacement after a second, so we would have to substitute all this into the equations of motion. Let's substitute these values into the second equation of motion. S B with respect to A is the final displacement, and the initial displacement is 0. The initial relative velocity v0 B with respect to A is minus 96.08 I plus 27.76 j. The acceleration of B with respect to A is 0, so this term will be 0. And we have to find the displacement after a second, so t in this equation would be 1. The displacement after a second turns out to be minus 96.08 I plus 27.76 j, and the magnitude of this is 100 meters. So after a second, A and B will be 100 meters apart. And this is as seen from A's frame of reference. A sees B traveling in a straight line with a uniform velocity. This is again very interesting. A and B are launched as projectiles in opposite directions, and their paths are not straight lines, they are curved lines, as you can see. So a person on the ground sees the projectile trajectories as curved parabolic lines. Yet when A observes B from A's frame of reference, A always sees B traveling with a constant velocity and moving in a straight line away from itself. And B would see A moving in exactly the opposite direction with the same speed. When two bodies are fired as projectiles, since they have identical accelerations, from one body's frame of reference, the other body will appear to be traveling in a straight line.